question, so it might be inconsistent. So if you find the grids does not align with the solution, you can approach me, and I will try to
Can I ask, is the, because I'm not in the mod, but is the midterm paper, is it on Canvas or like did he upload?
I think the solution is, but the paper.
Oh, okay. Then I'll check it out. Yeah, I'm just a guess.
Okay, so let's start. In this we'll be talking about reductions. So basically, reduction is how you solve one problem using the solution from another problem. So let's say you have a problem A and problem B. And say that if you can, given an input of A, say input of A, you can manage some function such that it becomes an input of B, and then you solve this input question B with respect to this input, and then you get some output B. Sorry, some output from B, and then you can convert this back to the solution from A. This basically means is a reduction of B. And if you can do both the coding and both this coding and this decoding in polytime, this is a polytime reduction. So in this case, we will denote as A reduces to B. And it means that the problem of A is inherently easier than B, or at most as hard as B. Okay, so let's look at some questions. Okay, so question 1. Basically, we are given a graph with vertices and edges, and we want to color the graph, but adjacent vertices cannot be colored in the same color. And the optimization version of this problem is that we want to try to find the minimum number such that we can color the entire graph. And there is also a decision version that you are given some number k, and you want to know if you can color the graph with at most k colors. I mean, inherently these two representations should be the same. And then we have a few statements for you to evaluate. Any ideas? Which ones are correct? Any other idea? So the result is actually all of the statements are correct. So this just shows that the decision version and the optimization version are actually equivalent. So let's look at the first one. So if we can solve the optimization problem in polytime, then we can solve the decision problem in polytime. This one should be trivial, right? So we just run the optimization problem in polytime, and then we check we check the answer with this k in O1, and this will give an polytime algorithm for the decision problem. Right? Any problem for this part? Okay, then for the second statement says that if we can solve the decision problem in polytime, we can also solve the optimization problem in polytime. This is also true because for the decision problem says that for each k, we can decide whether we can use at most k colors in polytime. And what we can do is that we can enumerate every k. So from 1 to so at both we will need at both v colors, right? So we just enumerate every k, and for each k we just run the decision version, and until we find the first k, and that will be the minimum k that is required in the optimization problem. Because each run of the decision problem is polytime, and we have linear number of scenarios to try, so the resulting algorithm will still be polytime. Of course, we can do binary search or something like this, but it's still polytime. Any question regarding this second statement? Okay, then the third one and the last one will just be the counterpositive of the first two. If you just take the counterpositive of the first one, you get the third one, and take the second one, you get the fourth one. So they will both be true. Anything unclear about the Q1? Okay, then we'll just proceed. Okay, for Q2, we have a partition problem, which says that so you have a set of integers s, and you want to divide the set into two parts such that they have equal total sum. This is a partition problem. And there is another problem called ball partition. So you are given k balls, and you want to divide the k balls equally into two ball players. And here we propose a transformation that transform a partition problem to a ball partition problem. As such. And is this transformation correct? If it's not, where does it fail? Can we reduce partition to ball partition? No, okay. So we first should know that we cannot, given any transformation, we cannot reduce from partition to ball partition because partition is actually harder. So there will not be any transformation that can do this. Partition, a ball partition is just you can because all balls are the same, you can just count the balls and partition, right? But for the partition problem, you need to do some summing and all that. So partition is actually harder than ball partition, so there will never be such a reduction. But the thing is that where does the argument fail? So for such a reduction to work, it has to ensure that a yes of this ball partition problem will be mapped to yes in the partition problem, and also a no in ball partition problem will be mapped to a no in partition problem. So it's like two conditions we need to check. And in this case, the second condition does not hold, which is a yes in ball partition does not necessarily imply a yes in partition. And we can see this easily by example, let's say W11 Fri. Right. And then we cannot solve this using partition, but we can solve using ball partition by using the sum of this 4 and be divided by 2 twos. Anything unclear about this kind of example? Okay, so just a side note that we can prove that yes in ball partition gives a yes in partition, and a no in ball partition gives a no in partition. We can also do, like, if we take the counterpositive of the second one, it will be a yes in partition implies a yes in ball partition. Right, so we can do this two as well. So these are these two options. A yes from AS implies a yes in S, and a yes in S implies a yes in AS. And do either way. Okay, so again, we'll be using this partition problem, and we have the knapsack problem from lecture. And now we want to divide a reduction from partition to knapsack. So for knapsack, we have values and we have base and values. We put a pair of the same value, and then we try to run the knapsack problem with capacity W as half of the sum, and also threshold V as half of the sum. And will this be correct? Again, to check for correctness, you only need to verify these two statements. So let's look at the first direction. Let's say we have a yes for the partition problem. So let's say the original set is S. Let's say we can, it's a yes, so we can somehow partition it into S1 and S2 such that the sums are equal. And then from here, how can we construct a solution for the knapsack problem? Is it possible? If we just take, so let's say this is W1, W2, for this S1. And then if we just take all of those in our knapsacks, we will have, so the weight, the total weight will be, the total weight will be sum of WIs, which will be 1/3 of the total sum. Right? And what about the values? The values we also, while construction, the value is the same as the weight, right? So still for values we have this, which is half of the sum. And half of sum is this is greater than, or if this is smaller than or equal to the total weight of W, and this is greater or equal to the total the threshold of weight. Actually, they are exactly equal. So we can take either S1 or S2 as our solution, and this will constitute a solution for the knapsack problem. So a yes from partition implies a yes in knapsack. What about the other direction? So if we have a solution in knapsack problem, that means we have a solution such that all the weights, if we sum them up, they are less than or equal to W. And all the values, if we sum them up, they are at least B. Right. But by our construction, the value and the weight are the same. So these two quantities are actually the same. So this is less or equal to this W, which is half of the sum. And this V is also half of the sum. So we have half of the sum less than or equal to this sum of Wi, and it's less or equal to than this half of the sum. So which means this is exactly half of the sum. And if we select those items, we will have a solution for the partition. Anything unclear about this reduction? So both will be yes. And what about running time? What we do is just for each, we compute the sum, and for each value Wi we just duplicate. So this will draw in polytime.
Do we need to consider the encoding, or is it not relevant?
Yes. So for encoding, let's see. Okay, if you do it properly, so we have, let's see, the max of this Wi is given by this n. So the input size is of you have 10 times log n. This is the input size. And the running time for this reduction is just for each of the Wi, right? You do the summation and then you also make a duplicate of it, right? So it's still for each Wi you need log n time to process it for each bit, right? And also you just process n of the Wi. So it's still linear. And if you take into account of the addition, like if you do addition, the sum might have longer lengths, but it should not exceed like n squared log n. It should be something like let's see, n log m plus log n, something like this. No, sorry.
N of x.
Yeah, yes, it is. So log s is at most n times n, right? So if every Wi is n, so this is n times m. So log m is bounded by this log m plus log n, which is still this is not linear, but it's still polytime compared to the input size. this Q tree. Okay, if not, we'll proceed to the last one. Okay, so let's say we want to find suitable locations for our chain restaurant. Right. So there are some options that we can choose from, but we don't want our restaurants to be too close to each other. So every two restaurants they should have at least the distance apart from each other. This is our setup, and we are concerned with how many restaurants can we open. Okay, if you abstract it in a graph, this case we are saying that we want to select vertices such that none of them are, so every pair is at least d distance apart. Anything unclear about this setup? Okay, so the first part asks us to reduce this to independent set problem. Independent set problem says that, so we have a graph, and so let's say if so we have a graph, and we cannot select nodes that are connected by an edge. So let's say if we select this node, then we cannot select this or this because they are connected to this directly by an edge. Right. So in this case, the independent set, the max independent set will be 2. If we set this 2, or this will be this 2. So we cannot select anything any nodes that are connected by an edge. And what's the max number of nodes we can select? That's the independent set problem. And this problem is actually NP complete, as we will learn next week. What we have in the result problem is that we want to find the maximum number of restaurants such that each of them are, each pair is at least d distance apart. And in this case, in this independent set problem, we want to find the still is the maximum number of vertices that such that each pair is not connected by an edge. Right. Any idea? Yes. The idea should be pretty easy to connect these two together. So we are both concerned with the maximum number of vertices. One is conditioned on that two vertices are at a distance at least d, and this one is concerned with the two vertices that are not connected by an edge. Right? So if we just draw an edge when the two distances are near, right, then we can convert the problem. So the solution is that we, for any pair AI and AJ, if their distance is less than d, then we draw an edge. And then after drawing the edges, we run the independent set algorithm on this, which finds the largest number of vertices that are not connected by an edge, which means every pair is of distance at least d. Anything unclear about this reduction? Okay. Again, this is still polytime because all you need to do is just to compute the distance of every pair, which is polytime. Okay, so next part is still based on the same setup. So basically, we are trying to argue that it satisfies this kind of substructure property, which means that, let's say NB is the largest set that can fit into vertex set B, and then if we take AI, which is this one, and the rest, if we exclude those points whose distance to AI is less than d, this will still be an optimal solution. So this is like the optimal substructure property in greedy and DP algorithms. So this one just represents that we take AI and we exclude all the points that are at most d distance from AI. And then for the rest of the point, we compute the largest of the optimal solution. how we normally argue about this kind of substructure property is that we assume not, right? We prove by contradiction. We suppose that this does not hold. Then we use some interchange argument to say that this that will improve our optimal solution. So that will mean that the optimal solution is no longer optimal, which is a contradiction. And this is the exact approach we're following here. So here we see that suppose this is not true, right? And then if we do not consider this AI, right, then the rest will still be an input on this problem. And for those that are near AI, they cannot be included in this suboptimal solution because that will inflict a contradiction with this AI. Right? So if we exclude those also, then we are left with this vertices, and the solution on this vertices has to be optimal, right? It's the same argument. Suppose this is not optimal. That means that we can somehow improve this, and we substitute this improved solution back to the original one. This solution will be improved, right? And it will not introduce any new conflicts because all of the points that are near to AI, they are already excluded in this solution. So that will contradict the fact that we start with an optimal. The typical strategy we use for substructure optimization. Okay, so now we simplify the question such that all the restaurants are on a single line and they are sorted based on their coordinates. And then we want to show that A1, which is the vertex with the smallest coordinate, it is always a part of some optimal solution. This reflects what we do in the greedy algorithm, right? We prove that if we do some selection, there will always be some optimal solution left. That tells us that we can actually adopt a greedy algorithm. So this will be the exact same problem as, if you recall, is the last one in tutorial 8, which is the context was, I think it's optimal scheduling problem using greedy algorithm. So for this kind of problem, we typically start with some random optimal solution. Then we try to say that if we somehow include this A1 into the solution, this will this will not harm. So we can convert any optimal solution to include this A1, and this will still be an optimal. So let's say this is an optimal solution, and it does not include A1. If it does not include A1, it has to have some vertices that is the smallest. And we can simply swap its smallest element with A1, and this will not harm. Because everything is at least D apart from the original choice, and if we further, if we move the A1 which is further away, definitely it will not conflict with any other one. And this might make you recall the argument we made in the frequency optimal scheduling problem. In which we argued that we can always swap the last activity with the one that starts at the very last. Okay, so in part B and part C, we have proved that. In part B, we have proved that it satisfies this optimal substructure. And in part C, we prove that if we reduce or if we simplify the problem on a single line, then it satisfies the greedy problem. That means that we can design a greedy algorithm to do this. Greedy property, how we design the algorithm is that we just use this greedy property over and over again to make our choice. So what we do is that we first sort all the vertices, and then we repetitively take the smallest one. Right? And then to avoid any conflicts, we just remove every vertex that is near this A1 from the list, and then we recurse to select another smallest one. This is given as this. Right, so in each step, we just add in the smallest element, and then we remove all the elements that has conflict with it, and we return. The greedy property tells us there is always some optimal solution that contains the smallest element, right? So if we select the smallest element, we will know that there will still be some optimal solutions that remain, right? And every time we take the smallest element, we know that there will be some optimal solution remaining. We repeat, right? Until finally, after we select all the elements, we are left with one solution. And we know that at this time, some optimal solution contains all those nodes remain. So that means this solution will be optimal. Any problems? Anything unclear about this? Okay, if not, that's the end of today's tutorial, and we will continue to study this reduction in the next one.